Hello there, grade 5 6s. Today you're lucky enough because I'm going to be taking your numeracy lesson. That is squares around squares. Now I'm excited because I think this lesson is going to be hopefully a challenge, but really kind of cool at the same time. Because I know you've been doing algebra this week, and one thing that I find is students get a little bit scared of algebra when these different letters start popping up throughout their equations. But really, hopefully what this lesson will do is it'll show you that all those letters is they're representing different parts of a problem or a pattern that's happening in the real world. And our real world pattern is going to be made with these squares around squares. So, just before we get started though, this question is a little bit misleading because when it says at the top what you need, it says you need 24 squares in one colour and then 12 squares in a different colour. And then with the picture, it looks like you've got those two colours that alternate. So like this one here where I've got blue, yellow, blue, yellow. But then just below that, it's got a little sentence here that says each new square is a different colour. Now that makes it sound like it should be something like this, where each new square, as we add the squares around each other, should be a different colour, such as yellow, red, green, and blue. Now when I worked on this problem initially and tried to solve it myself, I started with this option here, where the colours alternated. But I ended up in a little bit of strife because when I got down to the second last dot point of the challenge, the formula I needed to solve that problem ended up looking something like this. Now, I think this might be a little bit beyond us because it did end up in the year 11 and 12 calculus area. So if you happen to have any parents that can understand that, I would love to get their feedback. When I try and solve it using this formula, it works out, but my syntax could be a little bit off. So if you've got any parents that would know how to solve this, I would love to see if it checks out. But for today, we don't want to worry about that because I know you don't have hours and hours to spend trolling through the internet looking at random different math symbols. So we're going to ignore that, and you're going to try and get some different squares of some different size colours, like I've got here. Now you can I'm lucky enough to be in the classroom and have actual squares, but you could just cut these out of paper and you don't even need to colour them in. You could just put Y for yellow, R for red, and G for green, and so on. So get yourself set up with your squares and then pause the video now, and then when you're ready, unpause it and we'll talk about the first part of the problem. Now that you have your squares all ready to go, it's time for us to start working our way through this problem. So, number one, start with a single square, and I've got my yellow one, and then build two more squares around it. But while you're doing this, I really want you trying to have a think about and notice any patterns that are happening. Okay, because we're going to be describing the patterns we find later on using algebra. Okay, now that you've built your square, it's time for question 2. Explain how to find the total number of squares you've used. So, see if you can record two different ways that you can find out how many squares you've used altogether. Okay, do that, pause the video now, and when you're done, unpause it. Now there's no real right or wrong answer in terms of how you can find out the total number of squares used, but I'm just going to share with you two examples. So the most obvious one would be to go length times the width, because we know when we times the length by the width, we get the area. So in this case, my length is 5, and because it's a square, my width is also going to be 5 as well. So I could work out how many squares I've used altogether by going 5 times 5 equals 25. So that's one way. Now I'm going to show you a different way. So for this extra way, I'm going to find the total by adding up each of the squares. So for my first square, now instead of writing the word square, I'm just going to do S for square. Because like I said, that's what algebra is all about. It's using letters to represent things in the real world. So my first square, there's just one. There's only one yellow one. For my second S for square, there is, well, we've got 3 and 3, that's 6, 7, 8. And then my final square, my green square, I've got 5 and 5 is 10, 3 more, 13, and another 3, 16. So I can write here my third square, and I've got 16. Now all I need to do is add these together. So 16 and 8 will get me to 24, and one more, 25. So you can see for both my examples, I both ended up with 25, but I worked it out in a different way. Our next question is, explain how to find the number of squares of each colour. Now, what I'm going to do for this one is I'm going to add a new row. Now, if you don't want to feel like cutting out a whole heap more squares, perhaps you could draw this in your grid books. And you might even for this want to even add a couple of extra layers. See how many extra layers you can get, because what we really want to do now is start to think about a bit of a pattern that's going on here. So I'm going to add my blue row just like that. So now for this question, we want to be trying wherever we can to kind of work like mathematicians. So I recommend for this one, you draw a table, because drawing tables can really help us try and find some patterns. So can you draw a table recording how many of each colour there is as you go through each of the colours? Alright, pause the video again and have a go at doing that, and then unpause once you're done. So hopefully you've had a go now drawing a table, and it might end up looking something like this. So this is my table here. So I've got my squares with the letter representing each of the colours. So we've got yellow, red, green and blue. Then to the side I've added up the totals. So for the yellow there was 1, for the red 8, green 16 and then blue 24. By putting our information in a table like this, we can start to see that perhaps there's a little bit of a pattern going on. Because here, if we have a think about it, 8 is 7 more than 1. So we've got a change here of an extra 7. But then what you'll start to notice is that our next two changes, from 8 to 16, well then that's a change of plus 8. And then from 16 to 24, again, that's a change of 8. So let's have a think about the next one, and I'm going to predict it's going to be 8 more. So 24, if I had to add 8 to that, I would end up with 32. See if you can now make an extra square and see if you get 32. And let's just say for this one, we might go P for purple. And we can also think about it as P for my prediction, which is 32. Once you've done that, if it does check out, think about, well, how come what's this 7 doing here to start with? Is it just because we just need that first one to get the pattern started? And then more importantly, have a think about and try and explain why each square goes up by 8. And that's where actually having the squares is really handy, because you can move them around to really kind of work out why is that pattern going up by 8 each time. So have a go at that, and when you're finished, we'll have a chat about it. Welcome back. Now hopefully you've really tried to work hard to figure out why does this pattern keep going up by 8 after the first one each time. Now, in case you haven't been able to work it out, I'm going to try and demonstrate it here. So I've got my 2 circles in here, but I'm going to try and work out why there's an extra 8 with my third one after I go up from my second one. So let's have a think about it here. With my second square here, if I slide those up and then slide those 2 up, well, I've got some gaps that need to be filled. And yeah, you guessed it, I'm going to need 8 more to fill those gaps. So 2, 4, 6, 8. Because I'll need 2 in here, 4, 6, 8. Now we're up to question 4. Explain how to find the number of squares in the outside border. Can you check it in another way? So really, we're trying to work out how could we add up all these squares in the outside border. Now there's lots of different ways we could do this, and I want you to really challenge yourself to see if you can find 2, 3, possibly even 4 different ways. Have a go at doing that now, pause the video, and after you've had a go and found at least 2, then unpause and we'll talk about some of the different options. Here are some different ways of calculating the outside border when I'm doing my third square. So I could go like this. I think this is the way I was adding up before. So I've got 5 on each side. So I could go, well, 5 times 2. And I'm going to put that in brackets because I've got 2 5s. Then I'm going to add, well, I've got 3 2 times. So I'm going to add another 3 2 times. Now if I had to work this out, 2 times 5 is 10, plus 3 times 2 is 6, and that's going to equal 16. Alright, that's my first way. How else could I do it? Well, this time, if I'll slide it back together, I'm going to do something different. I'm going to take my 4 corner pieces out, and now you can see I'm left with 4 times 3, and then my 4 left over. So a second way I could go is I could go 4 times 3, and I've got my 4 3s, and then at the end I just have to add 4. Now looking at this, I don't actually technically need the brackets this time, because if we're doing our BODMAS, we're going to do our multiplication first anyway, and then add our 4 on the end. So that could be a second option. Now likewise, I might do a tricky option for this third one. I might go, well, 5 squared, because I've got my 5, so I might go 5 squared, because that's going to give us a total. But then I'm going to take away 3 squared, which would be the whole middle section. Take away 3 squared. Now order of operations, we're going to do our powers first. So 5 squared is 25. Then take away 3 squared, which is 9. 25 take 9 is going to be 16. Now they're just 3 options, but there's lots more different ones. So I'm sure you might have done it in a different way, and that's totally okay. Now it's time for question 5. Now basically I'm going to completely leave this up to you. Question 5 is basically going back through all the same questions, but instead of starting with a 1 in the middle, we're going to take that apart, and you're going to start with your first square being 4 like that. And then your next square will obviously go around that starting 4. So as you're going through these questions, think about what's the same as last time, what's different. Okay, so pause the video now, work that all out, and then we're going to talk about the challenge where the real algebra comes in. Alright, good luck. So now it's time for our challenge, and this is where the real algebra comes in. Because what we have to do in the challenge is answer the following questions, and we're just going to start with the first one. So if someone told you any size for the largest square, explain in 2 ways how to find, well, firstly, the total number of unit squares used. Now the first part of that question, if someone told you any size of the largest square, now what is the size? Well, I've already recorded on my square the 3 different sizes of each of the squares. So a red one has the size of 1, because it's 1 long. The green one has the size of 3, because it's 3 long, and then the blue square has a size of 5 because it's 5 long. Now, if I started to wanting to record that, obviously the size of the square, that's going to change. Every time we change the size of the square, the total amount of squares we use will also change. So both these things are what we call variables. Now variables are numbers that are the numbers that change when we put them into a rule that we're creating, and hence why we end up using algebra. So instead of writing 1, 3 and 5, I want to make a rule that'll work for any square, no matter what the size. So instead of using a specific number, like 3, 5, or even a larger number for a larger square, I'm going to use the letter S. That way, that S can represent any size. It could be swapped in for a 1 if we wanted to find out the total amount of squares used when the size is 1. Or later we could swap that S with the 5 to work out what's the total of squares used when our largest square is 5 long. So this is what I mean by this is a variable. We're putting an S, which is always going to mean the size, but the size is going to change depending on what size square we use. So what we need to now think about, and what I want you to think about, is what do you have to do to the S so that after you've done some calculations, it's going to equal the total. And then you should have your completed rule. So have a think about what you did before when we had the 5 and we had to calculate the total area. Think about the same things you did here and see what you can fill out here so that whatever you do to the S ends up giving you the total. Have a go at that now. Hopefully after having a go yourself, you've been able to work out the rule and kind of match it to what you did before. And that to find the total, all we have to do is simply multiply the size by itself. So the size multiplied by the size will give us the total amount of squares used. So let's just check now that we've got our rule, let's check and put in some of our answers. So if the size is 1 long, well 1 times 1 equals 1. And we've got 1 square. Now let's try for our size of 3. So you can see here that the S is the variable because we're putting different numbers into it to see different totals. So now we're going to go 3 times 3, and that equals 9. And yes, well we've got 3, 6, 9. And then lastly, let's try our 5. So we're going to swap our S with our 5 multiplied by 5, and that's going to give us our 25. So you can see that this one rule is going to work and help us be able to find the total no matter what size the biggest square is. Even if the biggest square was 50 long, then we would have 50 multiplied by itself, multiplied by 50, so I think would end up with something like 2,500 would be the total. So this is a rule now that we can use for anything. Now we've finally reached the last 2 dot points on the challenge. But it's important to note that when we started this problem, we decided to go with this variation where we've got a different colour for every single square. Which means at the second dot point, can we find a rule for the number of unit squares of each colour? If we had done this option, this was the one I had trouble with because I had to find a rule that would add every second square of that colour together, and that was the real challenge. So really, that dot point when we're going with this variation is basically going to be the same rule as the third dot point, the number of unit squares in the outside border. All you've got left to do now is to try and work out 1, 2, 3, maybe even 4 different rules that you can use to total the outside border. And the way you can do that is maybe using the letter B for border to represent the border. And then just as we did before, we're going to use S as our variable for the different size. So whether it's a size 7 square, a size 3, or even a size 100 square. So what are we going to have to do this time with our size to equal the border? Okay? Instead of last time, what we did before was we multiplied S by itself to get the total area, we're going to have to do something different to get the border. Now think back to when you just were calculating one of the particular borders and some of the kind of equations you were using. How can you put those equations in here representing some of those numbers as the letter S? Alright, pause the video now and have a go at that. Welcome back. Hopefully you've been able to find lots of different rules. What I'm going to do now is just share some different ones that you may or may not have came up with. But good job today everybody, and I'll see you next time.